at this point that I receive Rn equals Sn plus Vn, and where Vn is right, and Sn so the battery of this thing is also dying. I just hope that we are able to pull through today. With P, sorry, Sn equals A equals P, Sn equals minus A equals 1 minus P. Fine. This is okay.
Yes, sir.
Yeah. So
Yes, sir.
therefore, Rn given Sn.
But can you share your screen again?
Yeah, sure. Visible now?
Yes, sir.
Equals 1 upon pi n naught by tb e to the power minus x minus a by root over tb, or y root over n naught by tb. Just keep it n naught by tb. Fine. Similarly, if Rn given whole square fine. These
Yes,
beasts
sir.
are okay. Now based on this, want to obtain an estimate S hat n of Sn based on Rn. Fine. So since we have to choose between S hat n equal to A and S hat n to minus A, let us pick some threshold lambda and say that S hat n equal to A if Rn equal to or Rn greater than lambda, S hat n equal to minus A if Rn less than lambda. Fine. Makes sense?
Yes, sir.
Because we have to choose based on. So on this line, I say that, okay, I draw a threshold line at lambda, that everything for all received signals that are less than lambda, I say that I sent minus a, and for all signals that are greater than lambda, I say that I sent a. Now you see that there is black on the left hand side of this, there is red on the left hand side of lambda, and there is black on the right hand side of lambda, right? So there is the possibility of error, or there is the possibility that now this gives us four distinct possibilities that one, or rather say fine Sn, right? These are the four possibilities. So this is correct, this is correct. This is an error, this is an error. Agreed? I'll write it
Yes.
simply. So Sn a s hat n equal to a, no problem. Sn equals a s hat n equals minus a, Sn equals minus a s hat n equals a, Sn equals minus a s hat n equals a minus a. So these two are correct, and these two correspond to error. And since we are communicating, since we are sending information, we want the least amount of error, right? Since we are sending information, we want the least amount of error, and so we want to choose lambda such that the probability of error is minimized. Fine. So the probability of error PE as a function of lambda is given as probability s hat n equals minus a given, sorry, plus probability s hat n equals a right? This is the probability of error.
Yes, sir.
Yes. So this equals probability Sn equal to minus a given s hat n. Sn equals a times probability Sn equals a plus probability s hat n equals a given minus a. times probability these beasts. Fine.
Yes, sir.
Equals probability. Now S hat n given minus a means Rn less than equal to lambda. Given Sn equals a times p. Fine. Based on the definition.
Yes, sir.
Plus 1 minus p times probability Rn greater than lambda given Sn equals minus a. Fine.
Yes, sir.
Integral minus infinity to lambda I'll just simplify the notation slightly. So I'm just dropping the n here for because otherwise it becomes one minus p times. This beast. Okay.
Yes, sir.
Good. So now we want to minimize this with respect to lambda. I am not integrating first because this is a Gaussian function and the Gaussian function is not integrable in a closed form. This you might know already, right?
Yes, sir. We have the table too.
Yeah, so there's a table and you might have to use it, but the Gaussian function is not integrable in a closed form. So because of that, we will do the minimization right now and we know that let me look at this. So just to confirm the expression. So any of you remembers this expression? Or should I look at it? Okay, I'll look at it afresh. Wikipedia, Leibniz integral rule. And this is f of x bx times d by dx bx minus f of x ax d by dx ax plus ax or del by del x actually, because this is a partial d by dx a x to bx del by del x dt. Fine. So you have done this earlier, or this is the first time you are seeing this?
Sir, we have done it earlier.
Yeah, we have done this.
Okay, so you know how to differentiate under the integral sign. And this is a Leibniz integral rule, and based on this, now if I look at the first term, so here ax equals minus infinity, so this, which means this term is 0. Fine. F r or a of lambda equals minus infinity, derivative is 0. F r given a is independent of lambda, it's this term is also 0, and b of lambda equals lambda whose derivative is 1. Agreed?
Yes, sir.
Yeah, so b of lambda is lambda whose derivative is 1, so we are left with just one term in this case, that is minus f of lambda So we are left with minus f of lambda here. Or actually we are left with minus f of lambda given a times p. Plus, similarly, if we differentiate this, we get 1 minus p times f of lambda given minus a. Fine. This is the derivative of this term with respect to lambda. So dpe or del pe by del lambda equals this. Okay. Rahul, Adit, you agree with this?
Yes, sir.
Yes, sir. Yes, sir.
Yes. So great. So this has to be 0. Or p f lambda given a equals 1 minus p f lambda given minus a. Fine. Or we f lambda given a divided by f lambda given minus a equals 1 minus p over p. Fine.
Yes, sir.
Now
Yes.
we substitute f lambda and f lambda given a and f lambda given minus a. So this 1 over pi and not over tb cancels out in both the numerator and the denominator. So we are left with e to the power x minus a divided by tb divided by e to the power minus x plus a whole square in the whole square denominator and not by tb. These terms agree or this is okay?
Sir, is that lambda?
Yeah,
It should be
lambda,
lambda
right?
instead of x. Fine.
Yes, sir.
Yes, sir.
So e to the power a whole square tb plus lambda plus a tb equals 1 minus p over p. Fine.
Yes, sir.
Taking log on both sides, natural log on both sides, lambda minus a whole square tb plus lambda plus a tb. Fine.
Yes, sir.
Lambda
Oh,
plus a whole square minus lambda minus a whole square equals tb. Agreed?
yes, sir.
2 lambda or sorry 4 lambda a equals fine. So this is the optimal threshold, which minimizes the probability of error. But in your textbook or Simon Hakin's textbook, they only deal with the case half. So when p equals 1 minus p equals half, this term becomes
0.
0. So lambda equals 0. So when the prior probabilities of both the symbols are equal, or both a and minus a being sent are being sent with equal probabilities, then the threshold is 0 and probability of error is lambda to infinity or rather 0 to infinity right? But thankfully, I'll just look at your textbook for this one result. Yeah, we define q of x as 1 upon root 2 pi x to infinity e to the minus z square by 2 dz. Fine. So 0 to infinity f r given a dr equals t tb pi n naught by tb root over pi n naught by tb times e to the power r minus a whole square by fine this beast. So let t equal r minus a then I1 equals sorry square root. There should be a square root in the denominator. Yeah, to infinity right. Fine. Similarly, you can show that I2 is also equal to q of fine. Therefore, probability of error equals q of a by but EB was defined to be therefore this. This is the probability of error in case a binary symbol was sent.
So why
And
was A replaced by EB?
a square TB was replaced by
Acha, acha,
EB,
okay, 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 okay,
but this
okay, got it, got it.
fine. So PE equals Q of, this is kind of a measure of the signal to noise ratio. Symbol energy divided by noise variance or noise power spectral density.
Yes, sir.
So you get this as, so this is also this, the probability of symbol error also depends on SNR. And I'll simply write out the Q function table from your textbook to give you an idea of how this behaves. Q function table. Yeah, so some properties. Q of minus x equals 1 minus Q of x. Less than x less than 1. This is a cumulative distribution function, kind of a cumulative. This is actually the complementary cumulative distribution function. That's why Q of 0 equals half. For large x, Q of x approximately equals 1 upon 2 pi x e to the power minus x square by 2, and MATLAB you can use Q function to call the Q function. The Q function table, where is the Q function table? That is important. So, oh, Simon Akin has the Q function table has disappeared from Simon Akin's textbook. Let me look at this one. So I'll just use the Q function table from this textbook and table of integrals. So I'll Google this for you and write out some values. So I'm just copy pasting this link for your convenience. You can also have a look at this. Copy UC Davies. So someone was nice enough to plot these. So you can look at this, and what we get is Q of 0 equals half, that we know. Q of 0.1 equals 0.6. 46. Q of 1 equals 0.15. Q of 1.5 0.06. 68. Q of 2 equals 0.02. Q of 2.5 0.006. 2. Q of 3 equals 0.0013. Q of 5, I'm just directly jumping to Q of 5, 2.86 into 10 to power minus 7. So the Q function actually fall. You can plot this for yourself. Actually falls off like this. This is log of x, and this is, or this is, so this is the y-axis. This is a semi-log y plot. So you see that you can actually look at this link and see that the Q function drops off after 2.5, or after 2 or 2.5, the Q function drops off rapidly. Say at 3.75, Q function is close to 10 to power minus 4. At 4, the Q function is close to 10 to power minus 5. 4.5, it's close to 10 to power minus 6, and so on. So this is how the probability of symbol error varies with the varies with the signal to noise ratio, and you know that this is the square root of signal to noise ratio. So you can say that probability of error anyway is Q of A divided by. So this actually varies as the square root of, so as the symbol duration increases, the the probability of error decreases as the Q function of the square root of the symbol duration, and it decreases as the Q function of the amplitude of the symbol duration. Oh, sorry, symbol amplitude. Fine.
Okay, sir.
So this is the importance of signal to noise ratio in digital communication, and obviously you see that for a large enough SNR, you can have a vanishingly small Q, or vanishingly small probability of error. So apart from the quantization error, you can have a totally errorless communication, which is not possible with analog signals. Agreed?
Okay, sir. Okay.
Yes, sir.
Yes, because there you'll always have some noise figure and all those things, but here you can actually manage to get a totally error-free communication. So keep the Q function tables handy for the quiz this time. So after this point, there is obviously there is the issue of intersymbol interference and the eye diagram and Nyquist's criterion for distortionless transmission and all that. And then there is there are digital modulation, because this is basically digital modulation in the baseband. Then we have modulation schemes called amplitude shift keying, phase shift keying, frequency shift keying that work in the passband, because for wireless or for practical communication systems, we have to work in the passband. So there are passband communication system techniques, but due to some person eating a bat in China, we won't be discussing those during this semester. So this ends the official discussion of this course. So now comes the other question, that a preview for the next semester. So all this time we have worried ourselves about transmitting information from the source to the receiver, but we have never stopped to ask ourselves, what is information? So any intuitive answer, what is information? Or how do you measure information, for that matter? You say something is more informative or something is less informative. You say that watching the same IPL match again is less informative than watching it the first time. You agree on this statement?
Yes, sir.
So, or
Information is something that has meaning, sir. Maybe.
yeah, information is something that has meaning. So what provides us meaning?
Sir, some
uncertainty.
order.
Uncertainty. The more the uncertainty about something, the more information will it have. Or the less likely something is, or if we talk in terms of events, the less likely is an event, the more information does it carry. So if someone walks up to you and tells you that, okay, Australia won another cricket World Cup, you would how interested would you be? You'd say, okay, yeah, happens every 4 years, except in 2011. And then someone comes up to you and says that, hey, uh, Bangladesh or Afghanistan won the Cricket World Cup. You would be curious because that sentence carries a lot more information than Australia winning the Cricket World Cup, right?
Yes, sir.
So the less likely something is, the more information does it carry. And so in general, the measure of information for a discrete event A with a probability PA is IA equals minus log to the base 2. So the less likely it is, the more information in bits does it carry. And we will base the next semester's course on this. Because digital systems are all about the information carrying capacity of thing, or digital communication is all about this definition of information. Or digital communication is a totally different beast than this analog communication that we have covered till now, or this principles of communication course. So we are open for
Sir, so
doubts.
the more negative something has, as the information is, the less important it is.
No, so there's so negative information isn't possible because probability
Oh,
of any
okay,
event
okay.
is
So
between
probability
0
is
and 1.
0 to 1.
It's log.
Okay,
Yes.
okay, okay, sir.
So the probability of any, so log of PA will always be negative. So minus log of PA is always positive. Fine.
Yes, sir.
Great. So we are open for discussion, including when do you want to start with the Viva? Saturday, Sunday, Monday? Not tomorrow because I need one day to prepare the schedule.
Sir, after the quiz.
After the quiz. So quiz is on Monday. So the quiz is on Monday. Okay, so we start with the Viva Tuesday morning, you say.
So what I mean, what will everything covered in class would be in the
Yes,
syllabus?
everything. So Viva is the comprehensive Viva, 15 minutes. So what I will do is I'll ask you your topic of choice. So we have covered so many topics, right? So you
Yes,
get to
sir.
choose what you want to talk about.
Sir, and
So is
what
it
is
okay if we prepare that topic in detail and I mean beforehand and then tell you about it?
So another thing is that you might have noticed that these topics are not totally independent of each other.
Yes, sir.
So you say AM and I might ask you about noise in AM, and from noise in AM we might go to the properties of noise. You might say I've prepared digital modulation and I'll ask you how PAM, pulse amplitude, how sampling is related to AM. You know how sampling is related to AM, right?
Yes, sir.
So if you have
Yes, sir.
a carrier signal in the form of a train of pulses, you get sampling. So,
Hmm.
so everything is interrelated, but it won't be that hard. I won't be that brutal. I'm just giving an example that prepare one topic as if your life depends on it, but cover the entire syllabus.
Okay, sir.
Okay, try to cover everything, but prepare one certain topic as if your life depends on that. Okay, because like as you
Okay, sir.
said, who told me in DSP you are being prepared to being asked to prepare one topic in detail instead of the Viva.
No, sir. I mean,
Yeah,
DSP, there are four
Only
options
for
for
a few
evaluations.
people.
yeah, okay. So, but
So
anyway,
you can either take the full syllabus or you can either choose a
yeah,
research question and prepare a
anyway you have
presentation.
to cover the whole syllabus,
Yes, sir.
because I won't stick to just one topic, but I'll give you the choice of starting the discussion. So you have faced the internship interviews.
Yes, sir.
Yes, sir.
So you have that experience that the interview always starts with the topic of your choice.
Yes, sir.
Yeah.
Yes, sir.
And then it goes sideways into things that you didn't imagine existed. Right? So
Yes, sir.
similarly, we'll start in your comfort zone and then see how large that comfort zone can grow. Obviously, the larger is your comfort zone, the better you are placed for anything. So I won't say I will take you out of your comfort zone, but the larger is the comfort zone, the better. And obviously, there is some point where everyone gets out of their comfort zone. You just have to ensure that your comfort zone is large enough so that the other party is also comfortable with it, or to accommodate the other party. So, end of syllabus.
Yes, sir.
Yeah, generally when I end the syllabus, there are just 10 or 12 people in class, so I take everyone for coffee. So go to the kitchen and get a coffee. All of you get a coffee for yourself. So yeah. Bye then. All the best for the exams.
So, sir, when is the Viva then from?
Viva, you said we start on Tuesday.
Okay, sir.
So I will. So, but if we start on Tuesday, then we'll have to continue till possibly till Sunday or the next Monday.
Hmm.
Please
Sir,
keep that.
again, in between there are exams.
Yeah. So see, uh, you just have to spare 15 minutes each student. So if you have some quiz or some written exam, we can exclude that time.
Thursday there is a
Yes, sir.
lab
Like
exam,
on
like
Yeah,
So
Thursday
5
there
hours
is a
of
lab
lab
exam.
exam.
So Thursday there is a lab exam, but I don't think everyone will be engaged with that at the same time.
Everyone will be, like,
Okay.
it's not
How
like
long
group
is the exam?
It usually goes from 9 to 12.
Okay.
And there is
And
also
then
a theory exam of the same subject.
Okay.
And
How is that exam?
time, like that usually goes for 1 hour, but the timings are not decided yet.
Okay. Okay. So it's a quiz. It's more of a quiz.
Yeah, like, yeah, yes.
Okay. Great. So see, uh,
can start on Monday, sir. I don't know.
so Monday, if you start, what happens is that I take the Viva from 9 to 12 or 9 to 12:30, and then from 2 to 4, and I stop at 4 on Monday.
Hmm.
Okay. So obviously, I'll give you time to prepare for the quiz. So I'll stop at 4 on Monday.
Okay, sir.
Okay. So should we start on Monday or on Tuesday? Because obviously, the later we start, the later we'll end. That is always there. And I cannot start tomorrow, because tomorrow we have this MTech project evaluation.
So let's start on Monday, because then we'll have Saturday, Sunday to prepare for the Viva also and for the quiz also.
Great. So let's start Monday. Okay then. Bye. Have a nice
Bye, sir.
vacation.
Bye, sir.